It's going. Okay, today we start a new chapter. We begin an assault on calculus. Okay, who gets a packet here? This is a very short chapter. So okay, what kind of homework you got tonight? No homework yet? It's every night tonight. Oh, tonight's homework is limits involving infinity. Okay, let's look at an example. Now, we already had experience with limits because we did this in the second quarter, yeah? Okay, suppose you have the graph of a function that looks like this. Suppose there's a vertical asymptote at x equals 3. And there's a horizontal asymptote at y equals 2. And so suppose the graph looks like this. And then what if I were to ask you, what is the limit of this function as x approaches infinity? That means when x is a very large positive number, the y coordinate is close to what? Does everybody see that? In other words, if the graph is going out to the right, the y coordinates are getting closer and closer to 2, because that's what the horizontal asymptote is, right? What is the limit of this function as x approaches negative infinity? So when x is a really large negative number, in other words, when the graph is going out to the left, the y coordinates are getting closer to 2, because that's the horizontal asymptote. What is the, you guys remember this from the second quarter when we studied rational functions? What is the limit of this function as x approaches 3 from the left side? So here's x equals 3. Coming from the left side, what's happening with the y coordinates of the graph? The graph is exploding down there. The y coordinate is like really large negative. So what do you think? Negative infinity. What is the limit of this function as x approaches 3 from the right? Well, here's x equals 3. Coming from the right, the graph is exploding upward. So what do you think the limit is? Infinity. So this is how we describe asymptotic behavior with limits. So tonight's homework, you're going to have limits involving infinity. So either the infinity is going to be over here or it's going to be the answer. Now, if you have the graph right in front of your face, it's pretty darn easy to figure out what the limit is, yeah? But you have to be able to figure out these limits without drawing these graphs. I mean, if you want to just imagine the graph in your head, you can. But in calculus, we have to be able to compute limits very quickly because all of calculus is based on a limit. That's why we study it. Okay, so let's do some examples. What is the limit as x approaches infinity? 2x plus 3 over 5x plus 7. Without drawing this graph, what is the limit? It's 2/5. How do you know, Mr. Burke? Because as x approaches infinity or negative infinity, we're asking ourselves basically what is the horizontal asymptote, right? Because whatever the horizontal asymptote is, the graph is going to get closer to it. And you guys remember the rule for finding horizontal asymptotes? If the degree of the top and the bottom are the same, you simply look at the coefficients. So the answer is 2/5. Easy. What is the limit as x approaches infinity of 2x plus 1 over x squared plus 3? What would happen if the degree of the denominator is bigger? Yeah, then we get the horizontal asymptote is y equals 0, so it's going to get closer and closer to 0. Okay, what would happen? Okay, I'm not going to do this. No, I think we should. What is the limit as x approaches infinity of x squared over x plus 1? What happens when the degree of the top is bigger? Yeah, you can divide, but the answer is either going to be infinity or negative infinity, right? So what happens when you plug in a really large number for x? Like a billion. You get a billion squared over a billion plus 1. Is that a really large positive number or a really large negative number? Yeah, so then it's going to be infinity. Right, that's because the graph, if you were to graph it, there's like a slant asymptote like that, then the graph, it's close, but it's going up, right? The y-coordinates are getting bigger and bigger without bound, so the limit would be infinity. So if you have a rational function, it's really easy. Didn't we just do limits a couple chapters ago? The only difference is it had n, now we got x's. That's the only difference. Okay, let's look at some other cases. What is the limit as x approaches infinity of tan inverse x? Now sometimes you just have to know what the graph looks like. Okay, some of us remember, some of us are still lazy on our inverse trig graphs. Now if I draw the graph for you, of course you're going to get it. This is what the graph of tan inverse looks like. So what is the limit as x approaches infinity? Pi over 2. What's the limit as x approaches negative infinity of tan inverse x? Negative pi over 2. Of course, if you have the graph, it's easy. These graphs have to be in your brain. Are these graphs in your brain? Okay, don't answer me. Okay, let's look at some more examples. What is the limit as x approaches infinity of natural log x? Think of the graph. Natural log x looks like this. As the graph is going out to the right, is it getting closer and closer to some horizontal asymptote? Or is it getting bigger and bigger without bound? Yeah, it just keeps on getting bigger and bigger and bigger, right? Very slowly, but it gets bigger and bigger and bigger. So what's the limit? If there's no horizontal asymptote, that thing just keeps getting bigger and bigger. What do you think? Infinity! Oh my goodness. What is the limit as x approaches infinity of sine x? Think of the graph. As the graph is going up to the right, is it getting closer and closer to something? No, so what's the limit? The limit does not exist. Okay. What's the limit as x approaches infinity? Oh, you guys think you're good, yeah? X squared over 2 to the x. Now, what happens when you plug in a really big number for x, like a million? You get a million squared, which is a really big number, over 2 to the million, which is also a big number. We call this an indeterminate form, infinity over infinity. It's a really big number over a really big number. So what happens when you have both the numerator and denominator both going to infinity? You have to figure out which one's going to infinity faster. And that's when you use n to the n. Oh, we did learn this, yeah? N to the n tuple. Except now it's actually x to the x tuple, but same thing. Because the only difference is we're using x's instead of n's, like we did when we studied sequences. So, you guys remember? What is that? That's a polynomial when you have x to a number power. Polynomial. What happens when you have a number to the x power? That's an exponential function. Which one goes to infinity faster? Exponential. So if the bottom is growing faster than the top, what do you think the limit is? Zero. Okay, you guys think you're good, yeah? What's the limit as x? We had this problem so many times, it's ridiculous. What about x plus 1 over x raised to the x? Can I do this? As x approaches infinity, the thing in the parentheses goes to 1. Agreed? Because the degree of the bottom is the same as the top, the coefficients. 1 to any power is 1. Wrong! Because this power is going to infinity. So you cannot do that. Infinity is not a number. Like if that was a 5 or a 10 or a million even, then the answer would be 1, but this is going to infinity, so what do we have to do? Yeah, we have to use the 1 plus box over n to the n, right? We gotta lomi, we gotta massage. So you remember what we did? Lift and separate. So you lift and separate. Hey, one, see, but the difference is now instead of n's, you got x's. Is that going to throw you off? Okay, well, I didn't even expect an answer. So you have 1 plus box over n to the n, except it's x's, so what's the limit? E to the box, e to the 1. Yeah. Oh, so Mr. Park, then we got to start categorizing again like we did last chapter. Yes! Not last chapter, 2 chapters ago. Okay, so those are limits approaching infinity. Let's look at limits when there's like a vertical asymptote, like this. What is the limit as x approaches pi over 2 from the left of tangent x? Now, sometimes you just got to know what the graph looks like. Is this a base graph? You bet your biffy it's a base graph. Tangent looks like this, right? Here's pi over 2, here's negative pi over 2. Tantor! So here's pi over 2, approaching from the left, what's happening? It's exploding upward, so the limit is infinity. So you just, hopefully you don't have to draw this, right? You just imagine it, right? Because it's a base graph. Oh gosh. What is the limit as x approaches 0 from the right of natural log x? I just drew this graph 5 minutes ago. It looks like this. So here's x equals 0, approaching from the right. The graph is exploding downward, so the limit is negative infinity. Okay, what is the limit as x approaches 2 from the right of x minus 3 over x minus 2? Is it? Probably. Okay, now, of course, we can draw the graph. You guys remember how to graph rational functions? Okay. What were the 4 steps to graphing rational functions? X-intercept. Quick. Too slow. 3. Y-intercept. Too slow. 3 halves. Vertical asymptote. X equal 2. Horizontal asymptote. Y equal 1. So the graph looks like this. So what is the limit as x approaches 2 from the right side? Negative infinity. But Mr. Park, it takes too long to draw the graph. Can I just like figure it out? Yes. Now watch. I'm pretty sure it's in the examples I taught you. I put it in the thing. Look, what happens when you plug in 2 for x? You get negative 1 over 0. Now, it is not negative 1 over 0 now. It's a number close to negative 1. And then you're dividing it by a number close to 0. What happens when you divide by a number that's close to 0? When you divide by 0.0000001, that's like multiplying by a billion, right? So it becomes really large. That's why the answer is going to be either infinity or negative infinity. So to tell when you have a vertical asymptote, when you plug in this number, if you get a non-zero number over 0, which is what we have here, that means there's a vertical asymptote there. That's because you're dividing a non-zero number by a number very close to 0. It becomes really large. Now, when you have a vertical asymptote, there can only be 2 possible answers, right? Either the graph explodes up to infinity or it explodes down to negative infinity. So when you have a non-zero over 0, that means vertical asymptote, the answer, it's a 50-50 shot. It's either infinity or negative infinity. How do you tell which one it is without drawing the graph? Yeah, well, if you read my notes, it says plug in a number very close to 2 on the right. Like 2.00001. What is 2.00001 minus 3? Just tell me positive or negative. Negative. What is 2.00001 minus 2? Positive. What's negative over positive? That's why the answer is negative infinity. Okay, let's try another one. What is the limit as x approaches 3 of x minus 1 over x minus 3? Oh. From the left now. Okay, how do I know there's a vertical asymptote? Because when you plug in 3, you get 2 over 0. Non-zero over 0 means vertical asymptote. Okay, so we know the answer is going to be either plus or minus infinity. It's a 50-50 shot. All you gotta do now is plug in a number very close to 3 on the left, like 2.999. What's 2.999 minus 1? Positive. 2.999 minus 3 is negative. Positive over negative is negative, and there's your answer. Now, if you don't believe me, just go ahead and draw the graph. Of course, you can apply the same principle to trig functions, yes? What's the limit of, as x approaches pi from the right, of 1 plus cosine x all over sine, no! 1 minus cosine x over sine x. Okay, how do I know there's a vertical asymptote at x equal pi? Because when you plug in pi, oh no, I had it right the first time, sorry. No, I have it right the first time. What happens when you plug in pi? You get 2 over 0. Non-zero over 0 means there's a vertical asymptote there. So at x equal pi, there is a vertical asymptote there. So coming from the right, it's either going to explode up to infinity or explode down to negative infinity. It's a 50-50 shot. How do you tell which one it is? Plug in a number very close to pi on the right, like pi plus 0.001. Okay, what is cosine of pi plus 0.001? Think of the unit circles. Pi plus just a little bit. What's the cosine of that? Like it's close to -1, right? What is 1 minus something close to -1? Positive. What is sine of pi plus a little bit? What's the sign in the third quadrant? It's negative. So positive over negative is negative, so the answer is negative infinity. So anytime you have you guys understand this? Non-zero over 0 means there's a vertical asymptote there. There can only be 2 possible answers, either infinity or negative infinity. You just got to figure it out. Now tomorrow, we're going to learn what happens when you have 0 over 0. What do you think happens? Well, you have to come to school tomorrow to find out. Okay, let me look at, I'm not going to say. Let me look at the homework. Let me see if I covered everything. Now there's going to be some problems there to separate the sheep from the goats. Come on! I think that's the exact same problem I just did. And if you look at tonight's homework, number 27 and 28, there's absolute value there. What do you do when there's absolute value? Okay, here, let's do one. I thought I trained you from the second quarter, but who knows? Maybe the training wore off. I didn't feed you enough donkey biscuits. What if I ask you this? Let's say you have a function with absolute value, I don't know, make up something. 2 absolute value of x over x plus 1, just make up something. What is the limit of this function as x approaches infinity? And what is the limit of this function as x approaches negative infinity? Well, what did I teach you? Whenever you see a function with absolute value in it, what do? Skip to the next problem. Pretend the absolute value is not there. Or make a piecewise function. Those are your 3 choices. You make a piecewise function. You go to calculus, you have to do this, people. I'm not going to calculus. Oh gosh, please help me. If the inside is positive, what do? You leave it alone. And if the inside is negative, you negate it. See, this is either equal to x or negative x. If the inside is positive, it's x. If the inside is negative, it's negative x. So here's the piecewise function. Now, if you want to find the limit as x approaches infinity, which piece do I look at? If the graph is going up to the right, which piece do I look at? Okay, so what's the limit as x approaches infinity for this one? What's the horizontal asymptote? It's 2. Now, as x approaches negative infinity, which piece do I look at? This one. So what is the horizontal asymptote for that? -2. Right? The degree at the top and the bottom are the same. You look at the coefficients. And of course, sometimes there's like top per kind of. Should I say that? I won't say that for the quiz. No, I'll give it, I'll show it to you now. No, I'm gonna wait. Okay, that's it. So this is a very short chapter now. So after tomorrow's lesson, that's kind of pretty much the end of the chapter right there. But then I think we're gonna combine it because then we're gonna start going heavy into calculus. Like I told you, why is calculus so important? Okay, you guys in physics. If you have the graph of, let's say this is the position, time versus position. Woo! This is the position graph. And like right here, what would the slope of the tangent line tell you? Who's in physics? You guys keep saying you're not. Oyadamari, you're taking the AP Physics exam very soon, right? If this is the graph of position, then the slope of the tangent line tells you
Instantaneous velocity.
the instantaneous velocity. Exactly right. So whatever the slope is, that tells you that what the velocity is right at that point. So see how the velocity changes, the slope changes every time? So in calculus, one of the first things we need to figure out is, how do I compute the slope of the tangent line? Well, you're going to find that out in a few days. And it has to do with limits. So in order to compute the slope of a tangent line, you have to be able to compute a limit, and that's what we're going to do. See, you guys who are taking physics next year, if you guys don't dominate, go to your room. Okay, let me pass out the test. Solutions are on the board here. I saw some travesties. You know, like this one, number 5. I gotta put this here because I would say about 8 people did this. So secant x, so this is a bozo no-no right here. This is a bozo no-no. Wait, I gotta turn off the camera first. I have this on the camera.